Okay, so here's another example. We're going to work out the field of a toroidal solenoid. So here you can see we've got a wire coming in and it's being wound all the way around this solenoid here, this toroidal solenoid coming out. So it's completely enclosed. It's like a long straight solenoid being bent into a complete circle. This figure shows a toroidal solenoid wound with wire carrying a current I. The paths 1, 2, 3 in this figure here are paths to which we wish to apply Ampere's law. Let's consider first path 1. So we're going to look at this path in here, path 1 to begin with. By symmetry, if there is any field at all in this region, it will be tangent to the path at all points. So we know that if there is a field, it's got to be tangent around here. The closed path integral of b dot dl will equal the product of b and the circumference L equals 2 pi r of the path. The current through this path, however, is 0. Hence, from Ampere's law, the field B must be 0. Similarly, if there is any field at path 3, it will also be tangent to the path at all points. Each turn of the winding passes twice through the area. So you can see that each turn here is going to pass one's going to be going, if you can see one underneath is going to be going in the opposite direction to the one at the top. So you're going to get one going that way and the one on the top going that way. So they're each going to produce a field. Each turn of the winding passing through the area bounded by this path carrying equal currents in opposite directions. Therefore the net current through this area therefore is 0, and hence B equals 0 at all points on the path. So here again we're going to have B equals 0. The field of the toroidal solenoid is therefore confined wholly to the space enclosed by the winding. So it's got to be in here only, okay, in this space here. Consider path 2. So we're going to look at this path now. A circle of radius r, again by symmetry, the B field is tangent to the path, and the closed path integral of b dot dl equals 2 pi r b in this case. So we see this, that equals 2 pi r b. Each turn of the winding passes once through the area bounded by path 2, and the total current through the area is Ni, where N is the total number of turns of the winding. Then, from Ampere's law, we've got the closed path integral times B equals U naught, and the total current is the number of turns times the current through one of those. So that's the total current. Therefore, B equals U naught, the number of turns, I over 2 pi r. The magnetic field is not uniform over a cross section of the core. So if we looked at a cross section of the core, it's not exactly uniform because the path length L is larger at the outside. So the path length L will be slightly larger because the radius is slightly smaller on this inner one. So we're going to have a different path length on both of these. However, if the radial thickness of the core is small, if this thickness is really, really small, in other words, we've got a very, very tight winding here, and that thickness is small. So if we say that N here is the number of turns per unit length, where 2 pi is the circumferential length of the toroid, then we can rewrite this as B mu naught Ni, just as at the centre of the long straight solenoid. So we can just use this, and we can use the same equation. The questions derived above for the field in a closely wound straight or toroidal solenoid are strictly correct only for windings in vacuum. For most practical purpose, they can be used for any non-ferromagnetic material. We can use this as long as we're talking about a vacuum, mu naught. When magnetic materials are present, the magnetization of the material causes an additional contribution to the magnetic field B. For paramagnetic and diamagnetic materials, all the relations between field and its source are still correct. If we replace mu naught by this general mu with Km mu naught, where U is the permeability of the material and Km is the relative permeability, the magnetic susceptibility Xm is defined as Xm equals Km minus 1. The tables of materials will list values of Xm basically and Km for many different materials, and that allows for the correct selection of mu.